So in an earlier video, we have seen the definition of responses that we can actually get from issuing queries in the knowledge base in the so-called ask operations. We also saw the definition of those responses when we tell something about the knowledge base. We try to add into the knowledge base about a sentence. In this video, what we will do is we'll actually now start looking at the algorithms that allow, if you like, this a machine to be able to efficiently do these kind of logical conclusions and provide, if you like, those kind of responses in a kind of an algorithmic kind of setting. And we'll see two algorithms out of the many possible. One is called model checking, so we'll see that model checking now. And also we will also see theorem proving as another category of algorithms that we can actually engage. So if we move now to this first one, which is logical reasoning through model checking, we have a situation where we have the knowledge base, and we ask something about, let's say, the P12. So we are actually go back to the, so this sentence P12 refers to the earlier video we've seen, the Ubuntu world. Okay, and we need to understand how the machine will be able to respond back to us with whatever it knows from the knowledge base. So it's either going to be true or false, or I do not know. These are the three responses we can actually have. And we're actually going to be issuing this query when the state of the world is at t is equal to 4. And if you go back to this kind of video, then we've actually had over here the sequence of actions. So we actually in this at this moment in time, and we are trying to understand at this moment in time how we are making this sentence, this inference. In this case, this inference will actually be true. So we're trying to see how we actually get this conclusion. Okay. So at this moment in time, we will be assuming that we have 5 rules. So we have rules 1, 2, 3, 4, and 5. So we will have this information in the knowledge base. So it's R1 to R5 only. And so let me write all this kind of information down. So we have the Ubuntu world with the following rules. So the first point is that the ask operation about the negative P12 is issued when the knowledge base is at t is equal to 4, and this moment in time, so at t is equal to 4, we assume we have 5 rules, let's say 5 sentences in the let's say R1 to R5 in the knowledge base. Okay, so if you go back and actually see what will actually be those symbols that are involved in these rules. So I have P11, B11, B21, P12, P21, P22, and P31. And the same, I can actually confirm, but these are basically the symbols we're going to have. So let's write them down. These are all the symbols that are involved in my rules at this moment in time. So we have 5 rules in the knowledge base, and the following symbols are involved. So this is P11, B11, B21, P12, P21, P22, and P31. Okay, so we have 1, 2, 3, 4, 5, 6, 7 symbols. So we have 7 symbols in total. Okay, and according to this kind of model checking approach, we will do the following. We will enumerate all models and this is, I will call these models with the index mi, and I is, since all the symbols are propositional, then the set of models that we actually have here, the number of models is 128 in total, so from 1 to 2 to the power of 7, which is 128. So evidently we'll go for a model where the state of the world is, the world model is going to be 0, 0, 0, 0, 0, 0, 0 to all ones. Okay, so we have here this kind of table. So I'm going to pause the video and come back to it. So in this table, which is also in your textbook, you can actually see here the 7 propositional symbols involved. And in addition to that, what we will have is for each of the 5 rules that we have stored in the knowledge base, we go ahead and using our truth tables that we have seen earlier, we are able to, for each of the rules that we have quoted in our Wumbus Word example, we can actually go ahead and determine the true or false value of each of the rules. Okay, so we actually write them here. As we have seen, the knowledge base is going to be satisfied if all the rules that we have inside it are satisfied. And therefore, we can actually determine the very last column. In this case, it is false because R5 is not satisfied. So the knowledge base is satisfied if all of the rules, so there is an AND relationship between those truth values over here that defines whether or not the knowledge base is satisfied. So we actually go ahead and for each of the rows of the of our propositional kind of symbols, we determine the corresponding truth values for our rules and therefore the truth value of the knowledge base, and we proceed all the way until we reach the 128th row. And actually what we can actually see here is the following. And actually let me write this some of this down so at least you have it. So we have, let's say R2 was as an example, we have the R2, the rule R2 being B11, if and only if P12 or P21. Okay, so this was the rule, and we have here, let's take the very first row. We have P12 is false. P12 is false, and P21 is also false. Okay, so definitely we have from that P12 or P21 is false, and therefore we have now B11. So B11 is false. So there is no, we also have B11 false from another rule of the knowledge base. The B11 false, I believe it was the rule 1, if I'm not mistaken. Actually, it was the rule 4. So we have There's no breeze in 1-1, so this was the percept received at that moment. Okay, moment 1. And therefore, okay, so we have this is of course false. So we have the following sentence: false if and only if false. Okay, so of course this is equivalent to false implies false and false implies false. So the false implies false is true, so we have true, and therefore the sentence, this rule R2 is true. Okay, so R2 is true, so we actually wrote it over here, and this was how we determine the true value of all these kind of rules according to this example. Okay, at least. Okay, so another thing we actually said is that the set of models, the knowledge base, is satisfied. And I'm actually referring now to the population of this column over here, when let's say R1 and R2 and R3 and R4 and R5 is true. Okay, and that's how we get to determine, if you like, this column. All right, so out of the 128 models, we only have 3 models that satisfy the knowledge base. Now that we have completed everything, we have 3 models that satisfy the knowledge base. And in all of these models that satisfy the knowledge base, the P12, the P12 is false. So the negative P12 will be true. So this is the final conclusion. Out of 128 models, only 3 satisfy the knowledge base, and in those three models, P12 is false. Therefore, what the knowledge base will respond is with the true, that there is no P, in other words, in P12. And this is how we came to define that value. That's how the machine will actually do it. Initially, in the Ubus video, we used our own kind of brain to do that kind of determination, but now at least we have one method, which is exhaustive model checking over here, that will allow us to do so. And sometimes, obviously, this model checking for more complicated words is going to take too long, and it's going to be fairly involved. So we will see a kind of an accelerated version of this algorithm that avoids us to evaluate all possible models, which is evidently exponential. So we'll start a discussion about the backtracking search, an algorithm that will actually help us alleviate the problem we've seen with exhaustive model checking in the first algorithm we have looked in an earlier video. And in this problem, I'll just present the problem on a kind of a real-life problem that it's going to be drawn over here. I have a printer, let's say, that has 3 positions, 1, 2, 3. That's a color printer, and receives red, green, and blue individual kind of cartridges. And the sort of a green cartridge, as a constraint, it has to be located in position 2 for the color printer to work. So let me write this down. And what we are going to do here is we are going to look at all possibilities that starting from and create, if you like, a tree, a graph that looks like a tree. And we will start with the nodes of this tree will be the locations. It's going to be either 1 or 2 or 3, and the edges will represent assignments to those locations. So by constructing a tree like this, we will see now how a backtracking algorithm is working and how we can eliminate all the possible possibilities of assignment and therefore reduce the assignment computational, the computational kind of load associated with this type of assignments. All right, so we have we start with the node 1, which is the location 1, and we definitely can go and let's say assign red for that location. We arrive at location 2, and we can assign green, and we can sort of go to location 3, and we can assign, let's say, blue. And then this is we arrive, if you like, at the termination point where we cannot really expand the tree anymore. So the second one is the second option that we have here, and temporarily we will ignore this kind of constraint, and then we'll revisit this constraint to see exactly what kind of branches of these trees can be eliminated. So this is green. We arrive at the node 2, and so on. We expand, but I actually forgot here to expand further. Here with red, green. This could actually be either green or blue at location 2 to arrive at 3, and then evidently this is green to arrive at a kind of termination node. Similarly, over here we have red and blue to arrive at 3, and over here we have blue to arrive to the termination node, and over here we have red. Anyway, it's kind of a very simple graph where now we have here red and green, actually green over here and red over there to arrive on this third node, and then we have red and green. And as it is evident now that we have that kind of constraint, we look at this kind of a graph, and we can actually detect here all the possibilities that are compatible with this graph in terms of terminate all the possible branches. So here you can actually see that this branch is definitely compatible to our constraint. This branch, and these branches are not. These assignments are not. And this is also compatible with our constraint. And of course, this is not. This is green over here. This is not. All right. So as you can see, the assignment, this evaluation of the complete graph could actually happen first, and then we kind of identified what is feasible or not. However, we could have eliminated this expansion already because definitely we have at location 2 we cannot really have blue. We could have eliminated the whole subgraph, if you like, if I may call it like this over here, and we could definitely have eliminated this. But this is, of course, a very simple example, and the number of nodes and possible assignments are sort of not necessarily that large. Evidently, given that the assignments mean the color here, we will now create and the nodes will correspond to locations. What we will do now next is to see how this approach is applied in this logical reasoning domain, where similarly we will be are able to eliminate a lot of the already existing from earlier infeasible solutions and expand only those who are going to be feasible. Okay, and that's really the gist of backtracking search to enable this kind of computational advantage. So I will, to make this kind of analogy a bit more evident, I have this kind of knowledge base. And in my knowledge base, I have the following sentences. I have more specifically 5 sentences. So I have the symbols, I will use the symbols Q, P, and R. So I have this P or Q, that's the first sentence. The second is P or negative Q. Then we have the negative P or Q. And then we have negative P or negative Q or negative R. And the fifth one is going to be negative P or R. Okay, so this is the equivalent situation we have here in this kind of knowledge base. And now, instead of nodes that we have here representing locations of the cartridges, the nodes here will correspond to the symbols, and instead of edges that corresponds to assignments to a color, then the assignments will correspond to a true or false value for the symbols that are on the corresponding symbol which is at the node. Okay, so I'm starting the evaluation. So what is really the question here? So the question is to come up with the set of models that satisfy the knowledge base. So that's the question, okay? The set of models that satisfy the knowledge base, and this using our earlier kind of notation is capital M of the knowledge base. This we are trying to understand what is this set. Okay, so from the get-go I'm telling you that there's going to be a negative result, so there will be no sets. The set will be null, but you know this is just a specific property of the specific example over here. But nevertheless, we will see exactly how similar eliminations of expansions could actually be applied by backtracking search. So we started with the symbol, let's say P, and evidently the assignments for the P could be either false or true. Then of course we can have the symbol Q here, and then of course we have also expansions in terms of R. So now that we have drawn this tree, then we can actually see here this for Q is equal to false, and this is Q is equal to true. And similarly over here we have Q is equal to false and Q is equal to true. And immediately actually we can see that one of the 5 sentences is not satisfied in this branch over here. The moment we have false and false for P and Q, then we can actually look at sentence 1, and we can see that this whole expansion over here is not necessary. And in fact, we are going to be terminating right here. And this will be an infeasible. I mean, the knowledge base is not satisfied because of equation 1, of the sentence 1. All right, so we have now, what about the true over there? Also, this whole thing is not satisfied. This whole expansion is not going to be needed because the moment we reach this point, false and true, take a look at the sentence 2. In sentence 2, we also have false because we have false or false. Therefore, this is also false. And therefore, if you recall, the knowledge base is not satisfied. In order for the knowledge base to be satisfied, then all of the sentences need to be true. And therefore we are going to not expand that one. because it's false. And then look at over here, then this whole branch also, this whole branch over there is also not going to be expanded. And this is because of equation 3. This branch, which involves P of equal to true, the P to be true, and the R, actually I forgot to write now, this is becoming important, R is equal to false here, and R is equal to true on the other branch. For this one, we will, the assignment true and R for P and false for R, this is because of 5 is not going to be satisfied. So definitely we see not a negative result here as well. And the assignment true and T makes the equation 4 false, and therefore we can conclude that the set of models for the knowledge base is the null set that satisfy the knowledge base is a null set. Yes, it was a negative result, but I hope you appreciated the function of the backtracking search, and your textbook has, if you like, a pseudocode associated with it. I prefer to do here the kind of a visual presentation of the of this kind of algorithm that effectively avoids the expansion and the exhaustive kind of model sort of evaluation in the sort of model checking approach we have seen.